Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my great pleasure to introduce Sean McLaughlin, who's visiting from CMU, and he will be talking about Intuitionistic Logic theorem proving. And I saw some of the slides. It also has DKAL, but I'm particularly excited to hear more about the polarized method and or polarized inverse method. Thanks.
Okay. Hi, thanks everyone for coming. I'm delighted to be here. Today I'm going to be talking about there's some pretty baked ideas and then some half-baked ones and then some just kind of sushi-like ideas. And the work I'm going to be talking about, the title is Automated Reasoning with the Polarized Inverse Method. So I'm going to be talking about basically theorem proving for modal logics using forward-directed search. There we go. Okay, so the motivation for this work is in authorization. So for instance, if you guys know about proof-carrying authorization, so a kind of common model for proof-based authorization protocols sent for the last 10 years from Appel and Felton in '99 is that if you want to, say, have access to a restricted resource, one thing you can do, one way you can organize your protocol or your security policy is you have some kind of protected API, and that the user, when they want to access a resource like a file in a system, they actually have to provide a proof that they're allowed to access the system. And the way this works, or it worked for them, is that you have some authorization policy written in some kind of logic, and then you have a principal like Alice who has some knowledge about the state of the world, and then once, say, Alice wants to access a file that's protected behind this API. So what Alice does is she executes some proof search procedure to prove that she actually has is able to access a file. Alice, after getting the proof object back from the proof search machine, sends that to the API. And then, while the proof search may be a very complicated thing, the proof checking is quite simple. So behind the API checks the proof that Alice actually has permission to access an object, and then delivers back the resource if the proof checks. So what I'm interested in is what kinds of things you can express, what kinds of policies you can express, so when is this useful, and then how do we do proof search? So let's just a simple example of what a policy might be. So we might say, okay, for all k and f, if the file f is read all, then k is allowed to read the file. So that's what the first sort of statement of the policy says. The second statement says, well, if the file has owner, only the owner can read it, and k is the owner of f, then k may read f. Okay, so pretty simple things you might expect to have to encode in some kind of basic file system security policy. Then you have facts like Alice is the owner of foo.txt, and then we might have some other statement that we have either proved or is just in some kind of proof database that foo.txt is either all read or owner read. So say we have a simple file system, all files are either owner read or all read. And then the question we want to ask, back to this part here, is the question is, can Alice read foo.txt? So clearly from this policy, she should be able to read it, right? Because she owns foo.txt, and if she's the owner, she's able to read it. So what other kinds of things might we want to express with security policies? So we might want to say, well, we might not. So the problem with this simple picture is that it's a problem if these proofs are if this knowledge is in one place while the users are sort of globally located. What we might want to do is encode modal logic. So ideas about something is true in a certain world, like Alice's world. So that leads to the idea of something like, well, a manager said that Alice can open a file. So what we want to say is that there's actually different principles in the world. They all have their own knowledge, and we want to encode that reasoning somehow. And this has a distinctly modal flavor. So then these principles may want to send messages back and forth to each other. So the manager can send a message to Alice that Alice may open the file. So then the policy would have to say something about the manager having permission or the rights to do this. Now, once we have that kind of system, we might want to say, well, how do we revoke permission? So we might say, okay, you have permission to read a file for a certain time. And that leads to sort of encoding domain-specific information in these policies. So like whatever time Alice is accessing the file has to be less than the time that the license expires before you can open the file. And this kind of thing is basically endless. One interesting one is, well, let's try to encode how many times Alice can open the file. So this leads to linear logic. So Alice may have a token and may be able to open the file once, but then once she uses it, that resource is gone. So if you're familiar with linear logic, this is exactly the linear implication of linear logic. And then a sort of silly example, which just says an example of how much further you can go. You can say, well, in ordered logic, what you can say is things have to happen in a certain order. In linear logic, you have to use a resource exactly once, but it doesn't matter. You can permute the context. In ordered logic, you can't permute it. So we might say, well, you have to put on your underwear before your pants and your socks before your shoes in order to be dressed. And so we can code, if we have a notion of ordered logic, we can encode these kinds of things in the policies. So the point behind these examples is that what you want to express, the expressiveness of your policy, is limited only by the theorems that you're able to derive automatically. So what this work is about is what kind of policies we can write. How do we search for proofs in whether a policy proves a query? So as a motivating example, I'm going to use DKAL, which is an interesting example that Nikolai pointed out to me when we were at a conference last month. So here's some examples of DKAL for those that aren't familiar with it. So you can say things like, so there's like I said before, there's sort of states of knowledge for each principle. So Alice knows if Chux is a licensed seller, and Chux says that Alice may play the file, then Alice may play the file. So that's a simple statement in DKAL. And then there's this message passing, which so one principal may send messages to the other, which they're actually sending a form of a formula. And then these communications can actually be predicated on knowledge of the sender. So here we just cared about what Alice knows. This just adds to what Alice knows about the world. Here you can also say, well, the bureau only sends this message under certain circumstances. Okay, so that you can get sort of arbitrarily more complicated. And then given a bunch of assertions like this in your security policy, or in your, well, I don't know what it would be in this case, DRM policy, then you want to determine whether the Alice can play the song or not. Oops, that should say song, not file. Okay. So what I'm going to be, the talk, my work is focused on intuitionistic logic, and so I want to try to make clear why we're using intuitionistic logic instead of the sort of more common classical logic. And the reason pretty much has to do with proofs. So in intuitionistic logic, when you have a proof of a disjunction, what you have is a proof of one of the disjuncts. And if you have a proof of an existential, you have a witness that witnesses that existential, unlike in classical logic. So, for instance, if I've got this statement P, and I want to show the proof that Alice has permission to read the file, well, there's a simple. This proof term always normalizes to exactly one thing. So if Alice can read the file, it's perfectly clear which elements of the policy led to her having that permission. So in other words, an intuitionistic proof tells us why Alice can read the file. And then it's easier to, so these policies can be complicated things. It helps us debug the file. For instance, if Alice shouldn't be able to read a file and you can prove she can, it can help us figure out what went wrong in our policy design. Now, in classical logic, you have some kind of normal form conversion, or you have equivalences like this one, and you really have no information about why a theorem is true. Another reason intuitionistic logic is interesting for me is that if you have an intuitionistic theorem prover, which I do for intuitionistic logic, then it's really quite easy to extend it to other interesting logics, one of which is DKAL, one of which is PCFS's proof-carrying file system. That's a recent invention from one of my advisor's other students. And then you can get theorem provers for free. So this is the sort of more half-baked work. With the theorem prover for intuitionistic logic, you can get theorem provers for linear logic and ordered logic. And this is a big deal because it's very hard to write theorem provers for these substructural logics. Ordered logic. It's a the socks thing. So the idea with ordered logic is that this is a conjunction, this circle, but the premises have to happen in order. So if this was in the context, what it would say was that you have to use the assumption underwear, and then use but you couldn't use the assumption in pants until you've used the assumption in underwear. So what it does is it takes exchange out of the structural rules of the sequent calculus.
Or the conjunction, right?
That's right.
And then. And then. You can call it and then.
Yes, exactly.
And that's it?
And then you have the ordered implication. So this implication, when you use the implication right rule, it will send this statement to the left or to the right of the context, there's a different arrow also. So the idea is that you have this ordered context. So you can encode things like Turing machines really nicely with ordered logic because you can just simulate the tape basically. So it's like linear logic takes away the contraction rule of the structure. Ordered logic takes away exchange. Okay. So the rest of this talk, I'm going to talk about how we do theorem proving for intuitionistic logic, and then which has been empirically quite successful, and then I'm going to talk just to show some applications. I'm going to show the application of DKAL and substructural logics. Okay. So the polarized inverse method. So what is this? So the inverse method. There's basically two ways of doing theorem proving. You can start with the goal and decompose the goal and try to prove the resulting sequence that that led to this conclusion, or you can start with the axioms and sort of work your way forwards. So the inverse method is a forward theorem proving search, similar to resolution in classical logic. Now this undirected forward search wouldn't be such a good idea, but there's lots of ways we can restrict what would be normally an enormous search space. And focusing is one of the most exciting that's come out recently, and we'll see some examples of this. It's a little bit technical, so I'm not going to show too in depth what focusing is, but I'll talk a little bit about it. The idea is that you use ideas from linear logic, and you classify connectives as synchronous or asynchronous, and then you can eliminate huge blocks of nondeterminism based on analysis of this synchronous, asynchronous behavior. Now, the polarized part of the polarized inverse method is that we can actually extend focusing to atomic formulas, which makes a big difference also in the search space. And I'm going to just briefly talk about my theorem prover called Imogen. So what is the inverse method? So here's generally what you would expect in the sort of, if you're setting out to prove a theorem, is you want to search backwards. So if you're trying to prove A and B implies B and A, you can use the implication right rule and then try to prove the axioms in that way. So the forward search looks a little bit silly. So it starts off with axioms and just generates all the possible facts that could possibly follow from these axioms. And it kind of seems like a bad idea. The idea is you maintain a database of sequence. You start with the initial sequence, and then you have some inference rules. You apply the rules, and then you hope to find the goal. Some people call this the British Museum algorithm, because apparently the British Museum has like pictures stacked like on top of pictures all the way up to the wall. Now, an important property of forward search, though, one of its saving graces is this idea of subsumption, which is really important in, for instance, classical resolution, where you note that some sequence, like this one here, gamma proves B, is actually strictly stronger than gamma and A proves B. So you can actually toss this sequence out. So that's going to partly save our forwards proof search method. And then we'll have to work with some term indexing to make this thing reasonable. So, okay, let's bash the inverse method, the forwards proof search, for a second. So here's one thing that looks really stupid, right? So you start with an initial sequence, A implies A. And then, well, there's the and right rule, and so then you have A implies A and A implies A. You can derive A implies A and A. And then you can keep doing this forever, and you'll never find your goal. We can keep this from happening by generating. We take advantage of structural properties of these logics. Like one is the subformula property, which says that you only ever have to generate subformulas of the goal when you're trying to prove them. So if A and A is not a subformula of the goal, then you can throw the sequence out. So this isn't actually a problem in practice. Another one is if we look at the rules of the sequence calculus, they look really bad from a forwards point of view, right? So think of the false left rule. So it says if you have false in your context, you can prove anything. So well, what do we put here when we're trying to do forward search? Do we just enumerate all the possible formulas that can occur? Well, we don't want to do that, obviously. Here's another rule. So this gamma, right? So we use gamma proves A and gamma proves B. But what should gamma be when we're going forwards? I mean, we somehow have to match the gammas up. This seems like a bad idea. And just the initial sequence has the same problem as the false left rule. So the solution is just to modify inference rules. And sort of in a simple way, you just take account of the fact that, well, you're proving things forwards, not backwards. So we invent a new symbol, which is dot, that just says false proves anything. And we combine contexts rather than forcing them to be equal, as in the backwards rule. And sort of the most important one is the initial sequence have no context, which completely changes what the meaning of the forward sequence are. So in the backwards methods, what the sequence means is that using these assumptions in the context, it's possible to produce a proof of A. So here, you get a slightly different reading, which is that all of these contexts are necessary to prove A. All of these formulas are necessary to prove A. So this gives you a slightly different reading of the sequence, but it makes forwards inference possible. So now, after kind of bashing the inverse method a bit, I'm going to say why I think it's a good idea. So, okay, the simple one is, okay, well, if you're proving A and A, well, in the backwards search, you would prove this twice. When clearly you only need to prove it once. And in the forwards direction, of course, you do. Now, this may not seem like it happens very often, but you can do more complicated things. So in the backwards search, you might have P of x and P of f of x. So here, you would first prove P of x and then prove P of f of x. In the forwards direction, once you've proved P of x, well, what you've done is you've proved P of x for all x. In particular, you've proved it for f of x with different x, f of x prime. So again, you only need one proof in order to prove this formula. Please ask questions stop me. I'm happy to if I'm talking too fast. Sorry?
To me, the worst thing in the Tableau method is the rigid variable searching.
That's right. It's coming. Yeah. Okay. So here, so what is the problem? Okay. So the question now is whether this is a forwards or a backwards arrow. What does this sequence mean when we're in the middle of the proof? So say we're searching backwards, and what this means to have a variable x is that we have used for all right rule, say, and we've got some variable. And the question is, what do we know at this point in the proof? And what I'm going to argue is that in the backwards proof, you know absolutely nothing at this point. And in the forwards direction, you know a lot. You know that this is a provable sequent. So what do I mean by you know nothing in the backwards direction? Well, okay, so we're proving an existential on the right. So we invent a, like Andre said, a rigid variable for p of x. And what we want to do is instantiate this x with something to make this true.
In what sense it's rigid?
Well, the point is that these x's are the same, so that any so that when we do the for all right rule, okay, right, these x's are the same. So when you instantiate this one, you also have to instantiate this one.
It's not local to a single sequence. It is global to the whole.
So let's see what happens in this case. So we're trying to prove p of xx, right? So the first thing we can do is unify. Okay, so we've got p of c and p of d shows p of x. So we can say, okay, well, let's unify x with c. So that change at this point, you now have to go back and change these x's to c's. And then you say, okay, let's solve the right-hand side. Well, q of c is not in the context, so we fail there. So we say, oops, and we have to go back and undo everything we've just done, which in this case is not too much, but can obviously be a big deal. And then, okay, well, then we actually can make the right choice and find that we can prove D. So now in the forward search, once you've proved the sequence, this is just a fact of life. It's a fact of logic, and you never need to reconsider anything. This is, another way of looking at this is that these variables are universally quantified outside of the sequence. So what you have is you've really learned a new fact every time you've generated a new sequence. Okay. So the point of this discussion is that the forward search is not crazy. Right? So we can take advantage of logical properties like the subformula property. A finite rule property just means you never have to generate an infinite number of rules from, or an infinite number of new things from things you already have. And a substitution property is the idea that these sequences are universally quantified on the outside. And then, like we said earlier, using redundancy elimination can help eliminate duplicated work, and actually can keep the database manageable. So one author put it well, I thought, when he says, the fact that redundancy elimination is even possible makes you think that the forwards method is superior, because in the backwards method, it doesn't, while it seems smarter at first, it's not clear how to do redundancy elimination or what that means at all. So the fact that you can have a big database that gets bigger and then shrinks dramatically in size is an argument for why it can prove harder problems empirically. And of course, resolution provers like Andre's vampire, being the most famous example, are superior in practice. And in our experience, intuitionistic logic, while not competitive at all with classical provers, it's compared to other intuitionistic provers, it's superior in practice.
So equality is a big thing with forward against backwards method. If you use equality logic with equality, then backward method are useless.
Oh, okay. So equality is quite tricky in intuitionistic logic too, anyway, but in classical logic, yes, indeed. Okay. So we can just step through a quick example to see this in action. So we're trying to prove P and P shows Q and P. Oops, P and Q shows Q and P. Okay, so these are the sort of the sequent calculus rules for the backwards calculus, and here's the forwards calculus rules that are derived from them. Oops, gosh, stop doing that. Okay, so the inverse method. So what I've argued for is forward search. Now I'm going to sort of make forward search more explicit and explain what the inverse method is, which is a refinement of forward search. So the idea is you take the forward search method and you further restrict what you can do. So here, the inference rules had a generic sort of meta variable here. But the inverse method recognizes that you can actually specialize the inference rules of the generic logic to the subformulas of the goal. So what you do is you actually generate specific inference rules that are sort of tailored just for a particular problem. and then you can apply those rules without having to do any kind of instantiation. So labeling is another aspect of the inverse method. So what we would do in proving this theorem is we would label the subformulas L1 and L2, so we didn't have to do complicated formula checking. We specialize these rules to subformulas in the axioms. And then and then this is our problem now, sort of a simpler looking thing. We're trying to prove L1 arrow L2 from these rules in these sequence. And we can kind of watch how we can use these rules to generate more and more stuff until we get the result. Now, so what we've generated here is L1 shows L2. So ideally, we have to contract this thing to get the goal, which leads to probably the biggest problem with the inverse method and forward search in general, which is the need for contraction. So contraction is this inference rule. It just says, well, if you have 2 copies of A, you can throw away one copy. So it's a very simple thing. Unfortunately, it's extremely complicated to implement. And the reason is that you can have nasty things like this happen. So if you have P of x1 and x2 and x3 shows this goal, well, there's lots of ways to contract this context here. So we can choose to contract these two, which would unify x1 with x2, yielding this sequent. Or we could choose to unify these two. Or we could choose to unify all 3. And these all leads to 3 different sequences that are not comparable in a subsumption relation. So in general, you can. So all the good things about the inverse method we've said. That the sort of worst thing about it is that you can generate thousands and thousands of contracts from a single sequence in this way. So full disclosure.
What does inverse in the name? Is inverse?
Oh, I think the inverse method just means that, like, normally, I mean, people search this way, and that the inverse of that is that. Andre, is that?
Inverse to backward?
Inverse to backward, yeah, I think so.
Inverse to the most obvious.
Inverse to the most obvious, yeah, that's good, yeah. Okay. Okay, so in summary, so the inverse method, the input is the forward inference rules and some goal formula. Now, this isn't specific to intuitionistic logic. This is just,
So the previous slide was about the contraction.
Yeah.
And so it's problematic, and that's it.
That's it. Yeah, unfortunately. I mean, maybe Andre has better ideas about it. But,
you just say this is the main pain point.
I just wanted to point out that this is not some panacea for all your theorem proving problems. Like you have these operations like contraction that it's really hard to see how to avoid. So sometimes it's not too bad. So for instance, you might.
The contraction can generate many different concepts.
Oh, exponential, right? So I mean, if you just have, you're getting n factorial here. Now, a lot of times, some of the contracts will subsume the other, so you don't have to keep all of them. But in the worst case, you do.
Okay.
Yeah. So when I ran this on the ILTP database, which is like the TPTP for intuitionistic logic, there was a couple of problems where I'm generating like tens of thousands of contracts. So they have these kind of weird examples where that are kind of trying to figure out these things about how to break your prover.
You can delay contraction.
Yeah, I'm hoping to. So right now I'd eagerly do it, but maybe there's ways using laziness to.
I might be wrong, but it seems that they should be avoidable.
Okay.
Because you can only apply inference rules in a certain order, and I can give you a paper about it.
Yeah.
And to give you an idea, okay, if say P of x occurs in a top sequence,
yeah.
there exists x, P of x, you know that you must merge them.
Oh, you must merge them all.
You must perform all of them.
No, but I mean,
so it doesn't matter in which order you do it.
But if you have an exists x, okay, so if it's an exists x, that's absolutely right. So if you have for all,
it's the same.
You might have to use a lot of times.
It's
right?
the same. If it is on the top level, you will have to merge them anyhow.
Okay. No. So maybe I'm not being smart enough here. But anyway, I wanted to point this out, and I'm very happy if I can get rid of this. Okay, so the inverse method, basically forward search, you label the formulas, you specialize the rules to the labels, you create a database, and then you search forwards. Okay, and the pros and cons we've talked about. Backward search is goal-directed and has very low space overhead, just the stack of the sub-goals you're trying to prove. The cons are you have this global quantification property where you're having to undo your unifications. And looping is basically impossible to detect without re-implementing a forwards-based theorem prover. So loop detection is basically just, well, if you're trying to prove, it just says if you're in the backward search and you're trying to prove something that you've already was an earlier thing in your stack, then you just fail because you're never going to prove it. You're just going to keep on trying to prove the same thing.
Isn't this technique called tabling?
Yeah, tabling, sure. Yeah. So tabling is quite expensive, and so I'm just saying if you implement loop detection, then your low space overhead pro is completely gone. So there are some tabled theorem provers that do this trick. Yeah. Okay. So that's, I mean, this is all old work. This has been done 50 years ago. But sort of we're interested in it now. Without any kind of optimizations, even though it's cool, the inverse method just doesn't work at all. You just generate far too many things. Now, what you can do, though, is you can get rid of a lot of this nondeterminism is completely spurious. And that's where focusing and polarization comes in. So first we make a distinction between don't know and don't care nondeterminism that I'm sure you're familiar with. So for instance, if you have a big chain of OR left rules, of ORs on the left, well, it doesn't matter the order that you decompose these ORs in. So you can just decompose them all eagerly and sort of throw away these disjunctive choices you could have made. The other kind is the don't know nondeterminism, which is harder. So if you have C1 or C2 or Cn, well, the question is, okay, use an OR right rule, and then you have another choice point. You either try to prove C1 or you try to prove this part, and then you have more of these choices. Now, what focusing does is well, people have been eliminating this kind of don't care nondeterminism for ages. What focusing does is it eliminates a lot of this kind of don't care nondeterminism, and that was sort of the brilliant discovery of Andreoli in 1981, I think, is that it's still complete if you can chain together these kinds of choices. So the technical details I won't have time to cover, but I'm happy to point you to papers or whatever. But the big picture is that when you write down a logic, and you're trying to prove a formula, there's this sort of space of all possible proofs. There might be many proofs of the same formula. If you eliminate inversion, you make your search space smaller, though there's still more nondeterminism that's extraneous. So using focus proofs, you get rid of even more of the potential proofs. And finally, with the polarization comes in is when you extend focusing to atoms, which is what sort of our novel part of this work. So we can think of now if we think of a proof as some big tree like this, a way to imagine the focus inverse method working is making the blue chains being the invertible rules and the red ones being the synchronous or the non-invertible rules. What you do is you make a bunch of choices. You start from you start from a red. This is just this initial case, and you go all the way up to the blue before you have to make another choice. So all of these are deterministic choices. And there's a nice example. So here's an example we'll see a little bit later when we're doing linear logic. And so this looks like some horrible proof. But with focusing, this is actually 3 steps. And so your theorem prover finds this immediately because there's only 3 steps to make, even though in the logic you're making a dozen or 2 dozen steps. And this works by generating what we call derived inference rules. So starting from from a synchronous non-invertible rule and making a bunch of steps, we chain all of these together in one inference rule, which we call a derived rule. So as an example, if you have A and B implies C on the left, you make this non-invertible choice. So you choose to prove C on the left and A and B on the right. You can continue making the choice A and B. And this becomes one inference rule. From A and B and C on the left, you can prove this.
So what you prove together, when you start with the red region, you include the red and everything blue.
That's right.
Above it.
That's right. So a proof proceeds.
And that's the definition.
And that's focusing, exactly. So what you do is each of these is one rule application from the blue, wherever the blues go, all the way down to the red that started them. That's one rule application. And in general, that can be sort of an arbitrary number of steps.
And the whole idea is that anything blue you can just apply.
Exactly. These are the invertible rules. It's like or left, which has been done. People have observed this since Jensen probably. And then sort of the focusing idea, the Andreoli, is he had the first proof that this is okay to do, which is, so an example is like if you have A or B or C or D, say, then it suffices to prove A. So this is kind of obvious, but it's hard to prove. So you get this thing. Okay. So you get 4 inference rules here, when before you would have a ton of choices based on, well, do I prove this one first or this one? And okay. So there's a lot of nonsense, a lot of extra choices that we're allowed to throw out here, which is what these red squiggles are. Okay. So like I said, so here's this proof that's actually 3 steps. So it's 3.
But what you're throwing out is a non-invertible.
That's right.
Followed by an invertible, followed by a non-invertible, but the non-invertible could have been combined. Yeah, right.
So here we're throwing out. This is a bunch of non-invertible rules, right? Here what you would. What the choice is okay, so normally what you would do with this subformula is you would generate these 2 rules. Okay, so this would be a rule in your database,
right.
And then so would this one, and then so would this one, right? And so what focusing is doing is it's throwing out the intermediate rules and saying we don't need them for completeness, which turns out to basically make the difference between whether this thing is competitive or not.
It just seems counterintuitive. Invertible rules with arrows, which have particular direction.
They're blue.
Sorry?
They're nice.
Oh, should I? Okay. Yeah.
Just go there.
Yeah, exactly. Just go there. So I stole this off the TXZ page. It was originally Feynman diagrams, and I liked it. It looked so good. I figured I would just keep it. Okay. So this is the big theorem. Well, it's sort of improved by Liang and Miller, but okay. There's a derivation of gamma proves A, and there's a derivation of gamma, a focus derivation. Okay. And then polarization is what you do is you see. So in original focusing, the atoms aren't given a synchronous or asynchronous meaning. I mean, since they're not rules, so there's no meaning to give them. And what polarization does is it forces them to be synchronous or asynchronous. Oh, sorry. Synchronous and asynchronous is the language from linear logic. So the idea is that a synchronous, if a connective is synchronous on the right, it means you have to wait. It means that it's non-invertible, roughly. Yeah. So it's like tensor on the right. You can't immediately decompose A tensor B without being able to know how to decompose the context.
So whenever you say asynchronous, I should say invertible.
I'm using asynchronous and invertible interchangeably. Yeah. Right. So really in linear logic, there's right and left invertible, or right and left synchronous, and right and left asynchronous. But right, the idea is I should be just saying invertible and non-invertible. So the polarization is another sort of detailed thing, but I just want to show, and I want to point you to the paper if you're interested, but I just want to show what a dramatic effect that giving an atom like plus positive or negative polarity can be. So here's like a logic, if you think of a logic program that plus 0 plus x is x, and if x plus y is z, then successor of x plus y is successor of z. So it's like everyone's first Prolog program. So what happens is if we make plus have positive polarity, then it generates these inference rules, which says, okay, well, if we read these in the forwards direction, well, if we have plus suck x, y suck z, we can reduce that to plus x, y, z. And this looks like it has really nice forwards behavior, right? If you have a plus 0xx in the domain, in the context, you can throw it out. And here you can sort of reduce something. Whereas if you give it negative polarity, what you're doing is reasoning on the right. So you start off with an axiom plus 0xx. And then from plus x, y, z, you generate plus successor of x, y, successor of z. So this is basically completely hopeless. You're going to generate every possible addition while you're doing your theorem proving. So, I mean, the idea is that if you choose the right atom polarity, you get sort of a linear program, and if you choose the wrong one, you will never terminate. So these ideas, this focusing in the polarity assignment to atoms, is sort of really essential to this forwards method. Okay, now.
So I can read the fourth bullet, see the paper, but since I have you.
Oh yeah. No, please.
So the point of this slide is that you have a predicate plus.
That's right.
And
so this is an atomic formula. That's right.
Atomic formula. Yeah. Now that atomic formula appears somewhere in the original code established. But then you make a point that if you include the top row of rules, the rule applications terminate.
That's right.
Whereas if you include the last two, the bottom two,
that's right.
The applications don't terminate.
Yeah.
But if we go back to that, we have some goal where plus can appear both positive and negative polarity. Is there any problem with choosing one or the other, or?
No, see, that's the interesting thing. What Liang and Miller showed is that, well, you can, in fact, as long as you assign a consistent polarity, like you don't arbitrarily choose each instance of plus to be plus or minus. You say at the beginning plus is positive, or plus is negative. If you do that, well, so you're given an input formula. Someone says prove this formula, f. Okay, so it has plus x, y, z in it. Okay. Now at this point you say, well, before I even start generating my inference rules, I have to decide whether plus is positive or whether it's negative.
Okay. So it has nothing to do with whether it's positive or negative in the formula.
Right.
It has to do with how your rules assign whether they appear.
That's right.
Operational.
That's right.
Positive.
Yes, so you're completely, the beauty of this, like what I find the beauty of this method is that you're free to sort of choose, I mean, you also have this with conjunction, right? You can choose this to be the linear with or the linear tensor. And so you're completely free to like, I mean, what you've done is you've refined the formula. Like one intuitionistic formula is like this dumbed down version of the 50 or, infinite number of formulas, of focus formulas, or polarized formulas it stands for. So if you choose the right one, namely where plus has been assigned positive polarity, then you'll prove this theorem instantly. And if you make the wrong choice, then it won't. But the beauty to me of it is it's not some kind of theorem prover optimization where you happen to do a term indexing thing right and you're using memory locality well and it works well. It's like this really deep logical thing where it says, I mean, this is a logical optimization. So it's a property of the logic, which I find really compelling. Please.
In terms of completeness, in terms of what you can derive with, are the top rules different from the bottom rules?
No. That's the hard theorem, right? So the hard theorem is that you can choose either, and they're still complete. And yeah, so I mean, so that's this 07 paper. So if you can, this says, well, you can choose anything, and it's still complete. So you've taken, you've reduced the search space from this huge thing to this sort of smaller one, but you've just hoped that you've chosen the right atom assignment because it's very sensitive.
Is that for any rules?
Any atomic formulas, yeah, that's right. So you make the choice independently for any atomic formula. So if you're given a big formula, then you have 2 to the n choices to make, 2 to the n options for how to sort of handle the atomic formulas, plus some other stuff I haven't talked about. You have more flexibility even. But the idea is that okay, so it seems like crazy, but I mean at least we have, even if some of the choices turn out to be bad, some of them are good, and so the science, or not the science, the art of it is figuring out which atoms to choose.
So in general, you have axioms given as clauses, and then you want to take the clause and then so the one on the left hand side is a unit clause, and you assign it to one of the signs in the sequence.
Yeah, right. So what this is assuming is that the input was exactly given as axioms. Okay, so you're given a bunch of axioms formalizing your theory, and then there's an implication saying, okay, this is the thing you want to prove from these axioms. So there's this pre-processing step where you say, okay, plus is actually positive, and then we can generate the rules to prove the theorem. And if you choose plus, you get these rules, and if you choose minus, you get these rules. So. Okay, Imogen is the name of our implementation, and it just implements basically what we've talked about. Sort of nothing that novel. We have it's kind of cool. We have a front end because it handles different logics, and then the back end does all of just the saturating search in a sort of generic way, and it produces natural deduction proof terms, so you can check that you're not doing something stupid. I'm going to skip this. So the results were pretty interesting. So the first propositional version we made as kind of a toy to see if the method worked, and then we checked it against the existing propositional theorem provers. And so this one, ITP inv, this uses this kind of cool n log n space decision procedure. So this one disproved one more than we could, but then we did pretty much better than the others. So here the green ones are the ones we could prove are not theorems, and the blue ones we proved were theorems. Not that dramatic, but at least we're saying, okay, well, this forwards method is competitive because all of these are backwards methods. So this is the only one that is forwards directed.
So it's very impressive propositional logic because the advantages of the inverse method are actually in the predicate case. So if you do this on the proposition.
Right. So this is all due to sort of the benefits of focusing here. Yeah. In the first order case, we are a little bit more impressive. So the best other one is this ILTP, which uses this connections kind of matings type method where you do you do a complicated unification. You basically take a classical Tableau theorem prover and you do this complicated unification on paths, and it turns it into an intuitionistic theorem prover using this amazing technique. But so we just ran this on this ILTP library, and we sorry.
A simple Tableau prover.
No, it is simple. It's very simple. Well, it's simple. It uses complicated unification though, because you can't just. It basically just takes lean-cop and changes the unification. So I mean, it's like this much code. It's simple.
Just a Tableau prover.
Yeah, exactly. Yeah. Okay.
So this much code where each line is this.
Yeah. But so Imogen still does better, and the interesting thing for us is that we're good at disproving theorems, at least in comparison. And this is actually really exciting because it's more important for us to be able to disprove things than to be able to prove them. And the reason is that we plan to use Imogen in an inductive theorem prover. So the idea is that if you want to prove an inductive theorem with sort of recursive types, you say try to prove it directly, and then if it says no, well then you say okay, well I is an int, let's do induction on I, and what you really want is you want to be able to know if the thing is going to be able to prove it directly before you do the splitting, and
when it disproves it, when it refutes it, it's because it's finitely saturated.
That's right. So it relies, unfortunately, so if it proves a theorem, it can produce a natural deduction proof term, which is nice evidence. If it proves something, it sort of relies on that the implementation is correct, because it's harder to produce evidence that something is not true. You could build like a Kripke model or something. It's a lot harder. So we've punted on that issue. But we just say, well, hopefully we implement it correctly. It's not true. Even if not, our inductive theorem prover is not going to be complete regardless. So we're kind of okay with even if we have a bug and there's some negatives. At least we're not saying something's true when it's not. But yeah. So anyway, this was good evidence for that we're on the right track anyway. So now I just want to, in the last few minutes, I would like to talk about a couple of applications. So one of the nice things about this is that the methods are completely general. I mean, we talked about intuitionistic logic, but we can really do a lot more. So DKAL is what I'm going to talk about. I'm not an expert in DKAL, and so this is my interpretation of what DKAL is. I've sort of simplified it a bit. And so I just want to point out some of the interesting bits. So you have this sorted first-order logic. And the first interesting part is that you have these interpreted symbols. So you have, say, less than on the integers and equal on the integers. And so, okay, so first of all, that's something we haven't talked about. I mean, that's something that's non-trivial to add. Like adding constraint domains to a theorem prover is like a whole field, which Nikolai is the expert in. So that's the first observation about DKAL. You have these constraints. The next is that you have these modal operators like we talked about earlier. So you have some principal, said f, implied f, and knows f. These are sort of slightly different things, and I'll show you the inference rules for them in a second. And finally, you've got these interesting communications. So you're passing. So Alice is telling Chux something, and so Chux is learning new information. And then the question is, you want to ask whether something is true based on a given knowledge. So the first thing you can do, so here you've got this nice authorization logic, and you want to express policies in them. So if you want to do theorem proving, you don't want to be messing with communications, because then you're in some kind of process calculus, and it's really hard to deal with. So what you can do is you can compile the communications away. So just by knowing what the meaning of the communication is, you can compile away these communications in sort of more or less complicated ways. And the idea is that after you've compiled these communications away, you are left with just a multimodal intuitionistic formula. So now at least you have a shot at using a theorem prover to prove these theorems. So.
Imagine you have a kind of global state.
Mm-hmm. Right, exactly. So what it looks like when you see these communications, it looks like there's some states like Alice and Chux, and they're passing messages back and forth. So when I first saw this, I got scared, because this looks a lot like pi calculus, or I don't know. How are you possibly going to understand these messages? But in the paper, they have this nice translation, which just says, well, if you just look at the semantics, these are actually equivalent. And so now you're back, like Yuri said, you basically collapse this into some gigantic world. Okay. Like I said, I'm not an expert, so
Okay.
I'll just say how I interpreted it. So in my interpretation anyway, so DKAL sub Sean is that you compile these things away. Okay. So that's the first step, and now we're at a theorem proving problem, And OK, we've got the old inference rules. But we also have the new inference rules, which are unusual. So they look a little bit like a modal logic K. So this first one says, OK, if W said gamma, then you can show that W said P if you forget about all the things that W doesn't say and just prove P from gamma. And then you've got a similar one, the exact same one for no's, actually. And then you have a weaker one for implied, which says, well, told just means it either said or implied. So you basically, if W said something in gamma or it implied something in gamma, you can use any of those to prove P. And this is where we get another big win from the forward search. Because in backward search, OK, so say we're at this point in the backward search. So you've got W said a bunch of things gamma, and then you have A implies W said B in a context. Well, this is a choice now you have to make. You can say, well, I can try to prove P from gamma and throw this out. So I can show gamma shows P. Or I can make a choice and add B to this set gamma and then prove A on the right. So every time at every step in the backwards proof, you're basically making a choice that might have to backtrack to. Whereas in the forwards search, it's just a deterministic check. You say, is W said all of these particular subformulas, are these subformulas of the goal? And if they are, then you make the inference. And if not, you don't. So you've eliminated a huge class of nondeterminism from the backwards search in the most trivial possible way. So that's where we are happy to make this observation that forward search is the only sort of way to do this. So the next thing, so now that, the modal constraints almost are really easy, actually, to handle. The difficult ones are constraints. And I'll try to briefly discuss why. So these are constraints like the time, sort of time of Alice is less than, some file expires in a certain amount of time. So one way to do this would say, OK, well, let's just add the axioms for less than to the theorem prover. And that's just not the right way to do it. And sort of our solution, which my advisor and I came up with another student, is to sort of we isolate the interpreted atomic formulas in a new context, and we solve these using some kind of external tool. So what we've got now is instead of a sequence like this, we add some constraints, and then we have a judgment that where one set of constraints entails another. So we can look at some of the rules for this. Some of them are kind of obvious. OK, so these are backwards rules. So you just pass the constraints to the subsequence, and here you combine the constraints. So this is kind of the obvious thing you would write down. The interesting ones are how you handle atomic formulas, because atomic formulas are all that ever show up in these constraints. So I'm basically out of time at this point, but the idea roughly is that any E constraint domain equation ends up in the constraints, and those constraints are solved using some kind of efficient tool. So here's an example of the thing at work. OK, we're trying to prove x equals y implies y equals z implies x equals z. Well, we first do a bunch of invertible rules, and we're left with this guy. And then these guys basically hop into the constraint domain, and then we use some efficient solver to run that judgment. OK, so our implementation for DKAL, so I made the implementation separate for DKAL because I was interested in trying out Haskell. It's about 6,000 lines. This judgment here for the constraints is sent to CBC using foreign function interface calls. And probably there's a better, using Z3 might be better. I'm not sure. Of course it is. Right now we can solve basic problems. I didn't have any. I'm hoping that maybe there's some data that's bigger problems, because it's hard to make any kinds of assessments if you're only solving really simple problems. But Haskell's fun if you guys haven't used it. And finally, I'm just going to whet your appetites, because I'll just give you a whirlwind tour of the kind of neatest application after DKAL that I've been playing with. So we can get theorem provers for free. So one of my advisor students a couple of years ago got his thesis for writing a linear logic theorem prover. And what I want to show in this work is that thesis is redundant. Exactly. So it's not my work. It's one of Frank's other students had this kind of brilliant translation of linear logic and ordered logic into intuitionistic logic. Oh, yeah. So maybe. So the idea for those of you who aren't familiar is that linear logic. So substructural logic just means you have these obvious structural rules that hold in classical intuitionistic logic, like you can swap the order around, you can combine things that are the same. So this throws the obvious thing out, and you get amazingly interesting logics. Like linear logic has been extremely fruitful. Ordered logic is less well known, but still kind of cool. Bunch logic is really popular because of its connection to separation logic. So the idea in bunch logic is that you have two different conjunctions, and that one's called separating and one's not, and they don't interact well, so you have to keep your context as trees. So that's what a substructural logic is. It just means it's one of these logics that doesn't obey the normal rules. The key idea that Jason Reed and Frank came up with is to encode formulas using sort of a specific domain, and then equations on this domain can simulate the structural rules that you're taking out of the logic. So what you have is these things called worlds and these things called frames. The worlds represent the resources in the context. The frames represent the conclusions, the resources in the conclusions. And then you have this encoding function that sort of ties them together. So the consequence of this is that if you can implement unification modulo the theory, then you get a theorem prover for free. So this unification modulo is quite hard, but if you can do it, then you get a theorem prover for free. So just real quick, you have this focused logic with the only difference is that you've got frames and worlds. And in linear logic, all this means is that you've got a star operator, which is associative and commutative, and it has this funny connection between frames and worlds. And then the idea is that if you do unification with respect to these laws, then you're not just simulating linear logic, you have an actual bijection between proofs in linear logic, focus proofs in linear logic and intuitionistic logic with these operations. So this is the translation. I won't go through it, but sort of each of these expresses. So for instance, we'll talk about the interesting one. So the interesting connective in linear logic is the implication. It means you can use the resource once. This says, okay, we'll translate this proposition P at a certain world and add that world to the resources used by N. And okay, so this basically the theorem is that this adequately encodes linear logic. And so this is the picture we saw earlier, and this is the linear logic proof, and this is the corresponding encoded proof, which looks really scary, except that since there's a bijection, really this is only 3 steps as this is. You can't see the 3 steps because I didn't color them, but yeah, they're basically those 3 steps. Okay, and then ordered logic, you just have a different worlds, different equations, but if you implement the thing, you get a theorem prover for ordered logic, which is another PhD thesis. Okay, so we've seen, in conclusion, we've sort of looked at how to prove things in intuitionistic logic, focusing and polarization, very important, and we can apply this to kind of cool things like authorization logics and substructural logics. And yeah, that's it. So if you see any problems that look like a protocol or a security policy that need proof search, then let me know, because I'm interested in more applications. Okay, thanks very much.
Thank you very much.
I'm a skeptic. You said linear logic was very successful. So one metric
Theoretically, it is, yeah.
One metric may be the number of dissertations written.
especially in Europe, by this metric, it is super successful. But was it really successful in any application, in any other?
Well, I guess it depends on how you define success. I mean, yeah. So, I think there's at least hundreds of papers written about it. So theoretically, it's interesting. I guess it. Can think of applications. So you can encode things like block swirl. I mean, you can encode lots of problems like planning problems, for instance, in linear logic in some trivial way. It's just that the theorem proving problem is harder than. So it hasn't seen a lot of industrial use yet, but it seems to be an elegant theory that's worth knowing about.
It's used in type systems to reason about unique pointers.
To write more papers.
Or tracking resources.
Chris has a paper.
Yeah.
Oh no, there's a tool. So there's this fractional types. So if you have like permissions, right? So fractional permissions. If you have one thing, you can split it up into half and half, and then you can only use the resource if you have full permissions. So this uses linear logic. So that actually has been used in Java. Yeah.
Programming system called Chalice that uses fractional permissions in that way. However, we translated to first order logic.
Okay,
so we can just do it there.
So Andre's putting linear logic out of business probably, but
it seems it's a Baroque way to incorporate counting.
Baroque.
Counting.
Perhaps, but Bach's like the best composer, so that's not an insult to me.
Thanks again.